Today, the theme of this video is, and maybe this is something you all already know about, but I didn't teach you for Java 1, so I don't know that you know it, so I'm just going to cover this as some basics. The topic for the video is algorithm versus data. Now, this can be tricky because algorithms and data are both things you find in code. So find both in code. But if you're not used to detecting the difference between them, you might just, all you see is code, and it's unclear what parts are acting as data and what parts are acting as the algorithm. So if I was to try to come up with a definition of data, it helps to break this down into two kinds of data. Because, and maybe you've heard this term before, there is what we call primitive data, and then there's the next level up, which I'm going to call complex data. And you're all in Java too, so you have actually seen examples of both of these. You might not know it if you haven't heard these terms. Totally fine. So I'm going to try to show you some examples of each of these. But first, just to jog your memory, I think you know some primitive types of data. For example, there are ints in Java. Ints, integers, numbers, floats, strings, booleans. And let's just stop at that, because with the idea of primitive data in mind, we can give a more precise definition for complex data in terms of primitive data. Because I like to define complex data as some grouping or structuring of primitive data. It can get more complicated than that, but let's just start with that. So I'll say a grouping or structuring of primitive data. And the reason it can get more complicated is a complex data can also structure other complex data. So I'll just say or other complex data. An example here might be something like so a string is primitive data. But if you're trying to model, let's say, something in the real world, not everything in the real world is naturally just one number or just one float or just one string or just one boolean. Most things in the world are best thought of as some combination of these things. So for example, a person might be a grouping of one integer, which is maybe their age, and a string, maybe their first name, and one other string, maybe their last name. You can get much more complicated than that, of course. There are many more attributes of a person that you could model by picking and choosing different simple data, primitive data. And just to give you an example of this or other complex data, maybe a person has a parent, like my mom is another person. So, you know, I can have a person as my mom. And so basically a person, in this case, well, let me just add both mom and dad. A person in this case, if we're modeling it to this level of detail, might have an age, first name, a last name, and might have another person that's associated with that person. And then, of course, now we have sort of a tree, because my mom, being a person, also has an age, a first name, a last name, and her mom, etc. So this is an example of how you build complicated data out of both primitive data and any other complicated data that you might have defined. All of that is an abstract definition that doesn't have anything specifically to do with Java or any particular programming language. This idea of algorithm versus data, you're going to find that throughout all of computer science, regardless of the programming language. So I think it's actually a much more important thing to understand than any particular facet of the Java language. But I will note that in Java, we define complex data by defining some class. So I'll just say in Java, we create classes to structure data. And those classes will have instance variables. And of course, in Java, we have methods. And the idea of methods here in Java captures another aspect of data that I haven't mentioned yet. So all I've mentioned is that you can sort of structure your data by grouping together other data. But there's another facet to data, which is that it can change. You structure it one way, but as your program runs, some stuff can change about it. An example here might be age, right? A person's age doesn't stay the same every year. You might add 1 to it to change that data. So depending on your data, whatever it is you're modeling, whether it's a person or a stack or a queue or an array list or a deck, etc. Whatever it is, it can often change. And the ways that it can change are captured usually in Java by its methods. So I will say in Java, variables are used to capture what the data is, and methods are used to manipulate that data and or query it. Okay, so that's just data, but algorithms and data are related to each other, so it's kind of hard to understand one without the other. So let's see if we can get a good definition of what an algorithm is. So if we were to define algorithm in terms of our current definition of data, I think a pretty good definition would be all the stuff you do with your data to solve some problem. So the particular algorithms you write are always tied to the data that you're working with. Let me write that down. The algorithms you write are tied to the data you're working with. Some examples might be, let's say we're working with strings. So you've worked with strings. You probably worked with them in Java 1 somewhat extensively. And if you've been doing problems on Code Wars, then you've definitely seen some strings. There's a lot of string problems out there. But given a string, there's various things in Java you can do with them. So you can create new ones. You can append 2 strings together. You can pluck out certain characters. You can slice them. You can say like, oh, I want just the substring between 0 and 5. So I'll say get substring. You can get their length. Whatever. These are all the things that you can do with a string. But when you're writing some algorithm to process a string, like let's say detect how many letter A's there are in some string, you have to do some combo of these various things. Maybe not all of them, but you'll have to do some of the things, the allowed operations on strings in some order with some logic in order to come up with the answer you want, like detect the number of A's. And that would be an algorithm. So example algorithm might be given some string, detect the number of letter A's. Actually, that's an example problem. It's an example problem. Given some string, detect the number of letter A's. An example algorithm would be some code or flow that does that. And it can be pseudocode, because usually when we're talking about algorithms, it's perfectly fine to write them in English and then implement them in Java. So pseudocode for how you might do this would be something like loop over the string, every time you see an A, update some variable, return that, let's say, integer, return that integer at the end. And then instead of update, let me say increment some integer. So again, I think you've all seen this from Java 1. But this is another example right here. So in order to solve this problem that involves strings, you have to actually use two pieces of primitive data. The string you're dealing with, the string you're trying to detect letter A's in, and while you're looping over it, you have to increment some integer. So what I'm trying to illustrate here is a common feature of algorithms, which is that depending on the problem, you're going to have to pick and choose which data you use to solve the problem. And then when you pick that data, you have to obey certain rules about it. Like with an integer, you can increment them. With a Boolean, you can't really increment a Boolean, so you wouldn't necessarily use that for this particular problem. Let's do another example. Let's suppose that so again, we're talking about how the algorithms you write are tied to the data you're working with. Let's suppose we're working with persons, as defined up here. So if the data is a person, what can we do with persons? Well, depends. It depends on what the methods are. So we know that integers we can increment them. We know with strings we can loop over them and we can detect characters in them. Those are things we can do with integers and strings. But persons are things that don't just come with Java. You have to define your own person class in order to be working with persons. So the things you can do with a person depend on the methods that you define in your person class. Just realized that my webcam is in the way of the text. Sorry about that. Let me make myself a tiny bit smaller here. Nope. All right, there we go. Maybe that's a little bit better. What was I saying? Yes, a person. What can you do with a person? It depends. So you can manipulate a person however the methods in the person class allow you to do it. So it's harder to give a list of all the things you can do, but I'll just say what you can do with an object of type person depends on the methods in the person class. But some possibilities might be set the age, or maybe increment the age. An example problem might be that given some person, find the combined age of both parents. So that's an example problem, which a solution might be get the person's mother, get the person's father, add their ages, return the result. That's an example algorithm that solves this problem. And that particular algorithm deals with a particular kind of data, person. Now, what if the data is a stack? Well, same thing applies. So if it's a person, what you can do with it depends on the methods in the person class. That's true for a stack as well. What you can do with the stack depends on the methods in the stack class. But stack is an abstract data type that was discovered long ago, and it has very specific conventions, namely that you can push and pop from a stack. So if in Java someone is implementing a stack, you can bet that there's going to be some method probably called push and some method probably called pop. It doesn't have to be that way. You can call it whatever you want, but that is the convention. So I will assume that. So if you're dealing with a stack, writing some algorithm that involves a stack, you're going to be able to, you can push to the stack. You can pop from it. There may be other things you can do, but an example algorithm might be, pardon me, an example problem might be, given a stack of numbers, find the sum of all the numbers in the stack. And this illustrates something very interesting about these data structures here. Let's go back up. Let's look at our, so we have primitive data, we define that. You can define your own complicated data like person. And then there are these other data structures that other people have defined, other programmers, those who came before us. They defined these data structures, and these have a particular name. These are abstract data types, or abstract data structures. And what that usually means, at least in Java, you've seen this syntax, where there's something inside of these diamond brackets, or these angle brackets. And in Java, what that means is that it's a stack of something, right? It could be a stack of integers. And so here, in this example problem, I'm saying given a stack of numbers. So in Java, that might be something like stack of integer. Find the sum of all the numbers in the stack. And that doesn't change this fact. I can still push and pop from it. It just constrains it. It means I can only push, in this case, integers, or I can only pop integers off of the stack. So these abstract data types are structures of other things. So you're going to have a stack of something, a queue of something, an array list of something, a deck of something. It's always going to have something else that it is structuring. And yeah, it can get really complicated because there's nothing preventing you from having a stack of stacks. You can have a stack of stacks. There's nothing wrong with a stack of stacks. In fact, it can get arbitrarily complicated. Just to freak you out a little bit, you can have a stack of array lists of stacks of decks of queues of integers. Now, is there a good reason for that? I don't know. Probably somewhere in the world there's a good reason to have a stack of array lists of stacks of decks of queues of integers. The point is, these abstract data types, you get to define what they're doing, and it can be arbitrarily complicated. That said, in this case, example problem, given a stack of numbers, find all the numbers in the stack. That one's not too complicated, so an example algorithmic solution to that problem might be pop all the numbers from the stack, add them to a total as you do so, maybe push them back, and return the total. That's one example. Okay, so with all that in mind, we're going to go into the homework, and we're going to look at what parts of the code are defining our data, and what parts of the code are defining our algorithm. So here we are looking at orders test, one of the Module 2 assignments. And let's look at test has next false. That's this method right here. So this method right here, this part of orders test, has already in it a few examples of something that's essentially data. So here we are creating our first taco, meaning we're constructing a taco impl, and we're saying that it's going to be a bean taco with cheese. And if we open up taco impl, which I have right here in this tab, we see that this class has very little algorithmic stuff in it. I don't know if you can see that, but let me try to tell you how I see this class. So I see this class as being very much a data class. And this is tricky in Java. You might find a class that's mostly data, or you might find a class that's mostly algorithm, and you can definitely find ones that blend the two. They're both, all three of those things are very common to see in Java. And if you just look at public class, you don't know. You have to kind of skim everything. But the reason I see this as a mostly data class is that the only things that really happen to it are you can construct taco impls, and when you construct a taco impl, the only things that happen is you store some data. So you store a protein into some variable, store a cheese into a variable. You don't process that data at all. It just gets stored. So that tells me that this class is mostly just doing data storage. Now, there is something that looks a little like an algorithm, and in fact, I think this is, I would consider this a very simple algorithm, which is that this class allows you to detect equality with other objects of the same type. So if you have a taco impl, you can check if it equals some other taco impl. And it does so by, here's the algorithm, this is the algorithmic part, it does so by comparing the order numbers. So that's the other thing going on in this class, is it's storing a random number that denotes the order number for this taco. And so here's a small algorithm. So even this simple class here mixes together two things. It's a data structure, protein and whether or not it has cheese, and an order number. It's got three primitive datas. Three primitive datas here. So we have a final UUID. We didn't talk about that. Didn't talk about that over here in my list of primitive datas, but that's one of them. But honestly, I think you can just think of it as a large number, right? It has a Boolean. That one we did talk about. That's a very common primitive data. And it has a protein, which you might say, wait a second, that's not primitive data. But it's an enum up here. And enums, I think you can just think of them as named numbers. Special, like, you could say, you don't really have to say that this is protein. You could say private int protein, and say that 0 will mean chicken, 1 will mean beef, 2 will mean pork, and 4, I lost track of my numbers already. You could assign different numbers to different kinds of protein, but the fact that it's easy to lose track of that stuff is exactly why we have enums. Java gives you this as a feature of the language where you can essentially say that there's 4 values, and we're going to name them with something that's human rememberable, like chicken, beef, pork, and bean. It's much easier to remember than 0, 1, 2, and 3. So that is also, protein right here, is also a primitive data. It's an enum. So to sum up, this class groups together 3 pieces of primitive data, so it is a data structure in and of itself, and it has a nice little algorithm encapsulated in this equals method that lets us detect if 2 of these data structures are the same. Now let's go back to orders test, because all of that was just looking at this line. So this method is an algorithm that tests some qualities of order Q impl. And the first thing it does is construct some new data. So construct a new data structure, the new taco impl, and then it constructs an order Q impl. Let's head over to order Q impl. Open declaration. Actually, I have it right here. There we go. So this one is also doing a lot of data structuring, but it has inside of it, this is where data structuring can get kind of complicated. This is a data structure that has within it another data structure. It has a deck of taco impls inside of order Q impl. This is a common pattern that in Java, a lot of Java programmers call it a wrapper class. W-R-A-P-P-E-R, wrapper class. Because this class wraps up a deck. And it's private, which means no one outside, like orders test, when you make an order Q impl, you have access to the order Q impl, but the fact that inside of it there's a deck, you can't really touch that from outside. From this algorithm, you're not allowed to touch this taco Q deck, which means it doesn't matter what methods there are on this, it's hidden. which makes it, sometimes that's a good thing. You don't always want there to be tons and tons of methods you can call because, as we saw earlier, when you're writing your algorithms, the algorithms you write are tied to the data you're working with, which means it depends on the methods in the class you're working with. And if there's 10,000 methods in the class, that can be hard to figure out which tool is right for the job. So an order QImpl does use a data structure inside itself to help it manage its own data, but it only provides for anyone who uses an order QImpl these public methods: hasNext, close next order, and how many orders. So only 3 methods. So it really simplifies from the outside. Anyone using an order QImpl doesn't have to worry about all of the complexity of a deck. They just, I forgot about this one, add order. That is also one of the public methods. Anyway, so the four public methods, and then order test has this algorithm that tests some of those. So it adds an order. So constructed a taco impl, constructed an order QImpl, added a taco to the orders, and then tested whether or not hasNext returns true or false. And I haven't implemented any of these methods, although you have, because you just did the homework. So my tests are failing, but yours are not. So in a moment we'll pop over to cards and deck impl, which is the other lab for this module. But just to hit home the point, we have here a class, orders test, which this is not a data structure class. And I can tell that because it doesn't have a single variable. It doesn't have anything that you can store in memory for this class. It just has methods that do stuff. Those methods are small algorithms that construct and manipulate data. So orders test is kind of an algorithm-heavy class. It's got code that is doing stuff with data. By contrast, taco impl and even order QImpl, I would say, are more on the data structures end of the spectrum for these classes. Their job is mostly to hold data, to store data, to structure it in a way that makes sense for the domain of taking orders in a taco truck. And so that's it. That's if you're gonna go out and be a Java programmer, that's skill number 1, is knowing how to take something in the world like a taco truck and thinking to yourself, well, what are the data structures that would capture something about how orders happen in a taco truck such that you can write algorithms that are useful. So let's go over to cards and see if we can see what classes are in use there and which ones feel like they're the data structures and which ones feel like they're the algorithms. I'll open up deck test. So deck test, once again, this is a test class, so it's mostly just doing stuff. It's doing stuff with data. So here's a quick algorithm that will check to see if deck has size of 52 after you construct it without jokers. So here, constructing some data, and if we hop into deck impl, we should see that it's another sort of data structuring class. However, anyone who wrote this create deck method knows that there's definitely some amount of algorithm you have to go through in order to construct a deck of cards data structure. So I haven't written it here, but most of you did. And you know that if jokers comes in and it's false, you'll do one thing. You'll add all the viable cards to the deck stack, excluding the jokers. And if it's true, you'll do the same thing, but with the jokers. For many of you, that involved looping over, this is the classic solution, and I think perfectly fine, which is loop over the various suits, loop over the various values, add the valid cards to the stack, exclude or include jokers if jokers is true. So that's the algorithm that many of you implemented, all in slightly different ways. I was impressed with with the variety of different ways that people essentially translated this idea in English into a Java algorithm. So this is a case of, this is like a class that mixes together some data structuring, got a stack of cards, and some algorithms that are required to create that data structure in a way that makes sense for the domain. In this case, it's got to have 52 cards or 54 depending, and it can't just be anything, right? They have to be very specific cards. A deck of cards has very specific things, like a Queen of Hearts you can assume will be in a valid deck of cards, whereas a Queen of Trees you would not expect to be there. So once again, just like the taco truck, this class exists to model something about the real world, meaning it's a data structure that structures data in such a way that it maps onto real physical things in the real world, like a deck of cards in this case. Now, I want to point out one other thing that is a commonality between the taco truck example and the deck of cards example. And maybe you noticed it because I mentioned it earlier, that this is also a wrapper class. So we have two wrapper classes here. We have deck_impl, which wraps around another data structure, one of these abstract data types, a stack. So deck_impl wraps up a stack, whereas orders_queue_impl wraps up a deck. Again, this is a very, very common pattern to see a wrapper class. So over here, I said that a person is some grouping of these things, and then I said that you can have abstract data types. Remember that these things can be kind of self-referential. For example, maybe I want to say that there is an array list of person, which represents a person's children. And that if I did that, and if I implemented that in Java, then a person would be in part a wrapper around some array list now of persons. So you can detect if something is operating as a wrapper class if it has usually some private variable of some other data type inside of the class. And then finally, we have the homework, which is deck linked list test. At least that's what I want to look at first here. Like all the other tests, this is a bunch of algorithms in every method. No variables up here. But if we see here, it creates a new deck linked list. So that was in the homework. And if we compare that with deck test, very similar, right? These two, here I am bouncing between these two classes, and you can see that only parts of it are changing. Everything else is the same, right? And I would say that brings us to the other learning goal of this module and even module 3, which is interface. So we see here that there's a deck linked list impl, which other than that behaves the same way. Like every algorithm here doesn't change. So here we're calling getDeck and size on a deck linked list impl, and here we're calling deck and size on just a deck impl. And the only difference between a deck impl and a deck linked list impl is what data structure it's wrapping up. That's it. That's the one change. So let's open up deck linked list impl. And we see that this one, deck linked list impl, has a deck of cards that is a linked list, whereas deck_impl has a stack of cards, which is a stack. So internally, inside of these two implementations of a deck of cards, it's different. What's under the hood is different. But what is outside, above the hood, is the same. And another way to say that in Java is that they have the same interface. They have the same methods, the same names, so that from the perspective of any algorithm that is using these data structures, it's the same. Because, like I said, the algorithms you write are tied to the data you're working with. And in Java, that depends on the methods in the classes. If the methods in the classes are all the same names, they take the same data, and they do essentially the same things, then, and here's the big point, is that you can swap one for the other and make minimal changes elsewhere. So if you have an algorithm that deals with a deck and makes certain assumptions about its methods, and swap it out for some other implementation of a deck, and the same assumptions will hold. You don't have to change other stuff. So most of you who did the homework, you said that these things implements deck, some more abstract interface. And that's Java's way of being able to capture and declare that your class has some particular methods. And I went into that a lot in my previous video, but just to hit home the point again from the previous video and this one, is the value of doing this is that it lets any algorithm be written as if it's dealing with a deck, not your specific implementation of a deck. So if someone wrote an algorithm assuming a deck, they can swap for one that uses a linked list internally, or one that uses a stack internally. And it won't change how the algorithm is written. So I'm going to write this down, and then I'll answer what I think is the big question, which is why? Why? Who cares? But let me write this down first. So this is a kind of a property of both algorithms and data structures. These are interrelated concepts, but I'll write it down here underneath algorithms. It's if you wrote an algorithm using one data structure, you can switch to another data structure that has the same interface without having to change your algorithm's code. If you wrote an algorithm using one data structure, you can switch to another data structure that has the same interface without having to change your algorithm's code. That is the selling point of an interface. If you're ever like, if someone asks you, why should we use interfaces? Or if you're wondering, why should we use interfaces? This is it in a nutshell. It's the ability to switch. It's the flexibility that comes from being able to write an algorithm once, and then if you realize later on, my underlying data structures are not good, as long as you used an interface to wrap up your decisions about what your underlying data structures are, like maybe you decided that you're going to use a stack to implement your deck of cards, and later on you decided, ooh, wait, no, I need to use a linked list. It's okay. You can just make the change under the hood, and everything above the hood, all the algorithms written using that interface, they stay the same. They don't need to care what's happening underneath the hood. But, okay, what's the big question here that I think you have, and I remember having when I learned about this stuff back in college, is why would you ever want to switch? So I'm saying you can, if you wrote using one data structure, you could switch to another data structure, but why? Why would you care? Why would one data structure be better than another? And this is a kind of deep question, and I'll give an example today to try to give you an idea of it. But let me point out that there's in many universities, this whole idea of data is often taught in a class, in a whole course called data structures. And this idea of algorithm is often taught in another course, often taught in a course called algorithms. Sometimes the names differ, but when I went to college, these were the names of the courses. I took a course called data structures and a course called algorithms. And in this Java course, we've got to kind of blend them together and learn some Java along the way. That's a lot to learn, so we can only sort of skim the surface of some of these ideas. But I'll give a shot at trying to explain what I think is the important stuff about data structures by answering this question. So why would you ever want to switch from one data structure to another? So if you start reading down the Arraylist docs, blah, 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 da, 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 come up to a sentence like this, which I'll admit probably seems a little bit daunting, but let's read it together. The add operation runs in amortized constant time. That is, adding n elements requires O of n time. All of the other operations run in linear time, roughly speaking. The constant factor is low compared to that for linked list implementation. You do not have to understand all of that right now. That is the kind of sentence that you generally understand after taking some course called algorithms, where you learn about a subject called complexity, which helps you understand this kind of stuff. Which is, it happens in O of n time, or this kind of stuff. It runs in linear time. The high-level idea here is that some operations on Arraylist are faster than the same operations on a linked list, and vice versa. Some operations in a linked list are faster than the same operations in Arraylist. So let's see if we can verify that. Let's see if we can detect, let's just write a quick algorithm and see if we can detect the difference between the speed of adding to a linked list versus speed of adding to an array list. And remember, don't lose track of the whole point here. The whole point is that, I'm not trying to prove that one of these is better than the other, because that's not true, actually. Linked lists are sometimes better. Array lists are sometimes better. And the cool thing about Java is that you're able to say that they both have the same interface, which means you can switch between them. You can switch between them if you pick the wrong one. So one, you don't have to stress out too much right now at this stage of your Java career about, understanding, when do I use this, when do I use that one? Because, as long as you're just using something based on its interface, you can switch if you decide you picked the wrong one. And if you're interested in the relative benefits of one data structure versus another data structure, that's the kind of thing you would learn in a course called data structures. So if you're interested, if you want to learn more, then you will have a chance to learn in this Java 2 course. Then if you're wondering about when should I use this data structure versus this other data structure, the subject you're interested in is called data structures. And oftentimes there are courses just called data structures. And if you're interested in how is this algorithm faster than that algorithm, then the subject you're interested in is called algorithms. And just as a side note, if you ever want to really level up your computer science, there's this Google search, open source CS degree. And there's this GitHub repository called OSSU Computer Science. And I think it's fantastic. So basically it goes through one potential sort of set of open source online free courses that roughly matches with what you would get if you went to a 4-year university and studied computer science. It talks about some core programming, core math, some stuff that many of you have probably taken at OC. Systems, theory, applications, etc. Let me search for data structures. Yep. So Introduction to Programming is where they cover simple data structures. Introduction to Computer Science, they cover basic data structures and algorithms and more. Core Math talks about more algorithms and data structures. Core Theory talks about even more data structures and very specific types of algorithms, like greedy algorithms. Talks about very specific data structures like spanning trees, more complicated algorithms like dynamic programming. This stuff gets real deep. You don't have to know all of it to get a job, that by any means. So don't let this stuff scare you, but let it inspire you. There's a lot of cool stuff out there, and a lot of it is free and easy to find, and this is a fantastic place to start computer science. Learn all about algorithms and data structures through many, many different classes that you can take in your own time. That said, let's dive into a very simple thing here, which is Arraylist versus linked list. I just made a new class here called Arraylist versus linked list because I'm just going to do a quick demo here. Let's say public static void main string args, and let's get ourselves one of each. Right? So let's say array list of integers. Just keep it simple. And we'll call it array list, and I'll say new array list. And then let's fill them both up with a lot of stuff. So they're both lists. Let's actually declare them both as lists because they both implement that interface. Let's make sure we import list. And then now that we know they're both lists, let's look at the list docs. And let's make sure that we only do to either one something that you're allowed to do with a list interface. So that's these methods. We can add. So it appends the specified element to the end of the list. Let's do that. So we're going to add a million things to one and a million things to the other. And we'll see which one is faster. I don't know. Let's find out. So let's say int I equals 0. And we'll say I is less than 1 million. I plus plus. We'll say array list dot add I. And it's complaining because I put these outside of my static method. Doesn't matter. We'll just move them inside of main. Okay, so now we have, let's print something out here. Let's say system.out.println. About to add 1 million items to an array list. And then let's do the same thing to a linked list. And then right when this one is done, let's print out done just so we know when it finished. And same thing, when this one is done, we'll print out done. Well, let's run it. Let's see if adding a million items is enough to detect the difference between the performance of these two data structures. I'm actually not sure if it will be. We might have to make the number bigger, but let's find out. Okay. They both happen pretty fast. Let's make it even bigger. Let's actually extract this number into a variable, just so I can change it more easily. So I'll say int max equals 1 million. I didn't think it was quite big enough to be able to tell, but let's run it one more time. We'll see if you can detect a difference between these numbers before I make this number bigger. Yeah, I think there is an obvious difference. It was hard to see, but this done printed out with a delay, whereas these two printed out very quickly. Let's do it one more time. A little bit. Let's make it bigger. Let's make it bigger and see if we can see a more pronounced difference. Oh yeah. Yeah, for sure, right? So we see a delay on both now, but I think the delay on these two is noticeably larger. Let's see it. Let's see it again. Oh yeah, right? Let's make it even bigger. Delay for sure. And then another delay. Still going. Still going. Oh, we're going to be here a while. Oh man, my computer's slowing down. I think my frame rate is oh, there it finished. Okay. I I don't know if my recording actually recorded during that cuz my CPU was churning. But there's a noticeable difference, right? And that's the point. That's the point. So let's say so So this is a very just simple algorithm that illustrates that even though we're doing the same thing, we're just adding to two different things that have the same interface. Because the underlying data structure is different, it's actually faster to add to an array list than it is to add to a linked list. Now, this has already been a pretty long video, so I'm not going to dig in right now to necessarily why that would be, but I will come back to this idea here. If you wrote an algorithm with one data structure, you can switch to another that has the same interface without having to change your algorithm's code. So if you decided you're going to use this linked list to store your 1 million elements, and then you found out that actually, ooh, it takes too long and your program is too slow, that's okay, because they're both lists and you can just switch. So why would you ever want to switch? Because sometimes one data structure is better than another in certain circumstances. That actually answers this question here. So why would you ever want to switch? Because sometimes one is better than another. Does that mean you have to go out and memorize which ones are better than others? No, because you'll absorb that over time if you keep studying computer science. And if now that you know that that's something to be looking out for, you can look out for it. You can ask yourself the question of when should I use this data structure versus another. So to sum up, in data you might have some complicated data structure, and sometimes you might decide to use a data structure because it literally models the world the way you want to. If you're talking about people in your code, then you probably want some data structure that's called person, that has the attributes of a person stored in it. Sometimes, though, you might have two data structures that behave in a similar way, like Arraylist and linked list. And you might prefer one versus the other based on its relative speed performance characteristics. But either way, it all comes down to what kind of algorithm are you writing? How fast does it need to be? What kind of problem is it solving? Those things will dictate what your data should be and which data structures you might want to use. And once again, if you are still confused and don't fully understand that, don't feel bad, because remember that algorithms and data structures are a core through line in all of computer science. You can sort of see it in this open source CS degree, where data structures and algorithms appear in many, many different courses. So you'll see it if you keep studying computer science. You'll see it all over the place. It comes up a lot. And that is why, actually, I made a recent change to the course structure. So we are about right here on array lists, generics, and iterators. We've talked about stacks and queues. I wanted there to be a little bit more data structures. So we'll survey sets and maps in module 4. And I nixed certain other data structures that although they're interesting like any data structures, I didn't want this course to be all about data structures. I wanted you to have some time to practice your algorithmic skills and skill building. So I added module 5, where your goal will be to get from 8th queue to 7th queue on Code Wars. And then module 6, which I think will be a challenge for many of you, but I'll work with you if you're having trouble. So don't let it scare you, just to try to get from 7th Q to 6th Q on Code Wars. This will require you to write a lot of algorithms that deal with various kinds of data structures. So you know what an int and a string and a float are from Java 1, but I know that many of you have not had a lot of experience writing a lot of algorithms that deal with these things, and that is an important set of skills. So that's why I didn't want this to be an entire course on data structures. I wanted you to see both sides of Java, which is both how to structure data in these classes like dec-impl and taco-impl, but I also wanted you to write some tricky algorithms, which is what Code Wars encourages you to do. So that's it for today, algorithms and data. I hope you enjoyed it, and I will see you next time.